It's easy to forget just how fast things changed. 2 years ago, when we talked about distant galaxies, most of what we said came with a giant asterisk. We thought we saw the first stars forming. We believed we had an idea of what early galaxies looked like. And when it came to alien planets, we were basically guessing, tracing shadows and hoping for the best. Then James Webb opened its eyes and suddenly the asterisk started disappearing. We weren't just detecting planets anymore. We were finding actual signs of what might be in their atmospheres. We weren't squinting at blurry dots from 13 billion years ago. We were looking at fully formed galaxies that, according to everything we thought we knew, shouldn't have even existed yet. And that was just in the first few months. Since then, James Webb has rewritten our understanding of the universe, one target at a time. From ghost galaxies that stopped forming stars billions of years before they were supposed to chemicals in exoplanet skies that don't belong there. If you were hoping for a telescope that would quietly confirm what we already believed, this isn't it. So let's look back not at the launch, not at the hype, but at the work, the timeline, the things it actually found moment by moment. Because the real story of Webb isn't in its design, it's in the discoveries. And some of them still don't make sense. We all saw the image and it looked like a starry wallpaper, nothing more than a tiny dot in the sky, magnified 100 times over. But once the shock wore off and people stopped saying pretty, the scientists started digging into the details. And that's when things got interesting. That single image, just one, showed thousands of galaxies. Not stars, not planets, galaxies. Each one filled with billions of stars of its own, scattered across an area of sky the size of a grain of sand held at arm's length. It was called SMACS 0723. A massive galaxy cluster located about 4.6 billion light-years away in the constellation Volans. But honestly, the name didn't matter. What mattered was what it proved. For the first time, we had a clear infrared look into the deep universe. And it didn't just show distant galaxies, it showed warped light, lensed arcs, ghostly shapes stretched across space and time. That warping wasn't an error. It was gravity. Massive clusters in the foreground were bending the light of even more distant galaxies behind them. And those distortions weren't just beautiful, they were useful. Gravitational lensing acts like a natural telescope. It magnifies. It reveals. It lets us peek behind the curtain. So in that first image, we were already looking at galaxies that existed over 13 billion years ago, just a few 100 million years after the Big Bang. That alone was impressive. But here's the part that caught everyone off guard. Some of those galaxies looked too bright, too structured, too evolved, and that didn't line up. According to most models, galaxies back then were supposed to be small, chaotic, and still forming their first stars. But what Webb showed, even in that first photo, was something that looked much further along: smooth structures, defined clusters, evidence of star formation that should have taken hundreds of millions of years, more than the universe had given them at that point. So naturally, the questions started piling up. Were these galaxies forming faster than we thought possible? Were our models of the early universe just wrong? Or were we looking at something else entirely, a different kind of structure built under different rules? And this was just day one. Before Webb had even locked in its full calibration, before its instruments had been tested across the board, it had already sent us back to the drawing board. Not because the data was unclear, but because it was too clear. It didn't confirm our expectations, it challenged them. What's wild is that this wasn't some deep survey that took months to complete. It was a snapshot, a glimpse, proof that even in the blankest parts of the sky, there are entire universes hidden in the dark, waiting, quiet until the right lens came along. That lens was James Webb, and in just a few hours, it rewrote our map of the early cosmos. A telescope like Webb wasn't built just to stare into the ancient past. It was also designed to look closer. Not at galaxies billions of light-years away, but at stars just down the street, orbiting their own little worlds we've been chasing for years, guessing their shapes, estimating their temperatures, watching their shadows. And up until now, that's all we really had, shadows. When a planet passed in front of its star, we'd see a tiny dip in light. That's how we found them. That's how we measured them. It worked, but it was limited. You can learn a lot from a silhouette, but it doesn't tell you what the planet is. It doesn't tell you what it's made of or what's in its sky or if anything's living there. Webb changed that. Its infrared sensitivity made it possible for the first time to read the actual chemical fingerprints of an exoplanet's atmosphere. Not indirectly, not through noise and modeling, but directly, by splitting the light that passed through it and analyzing the spectrum one wavelength at a time. That's how we got the first clear detection of carbon dioxide on a planet outside our solar system, WASP 39b, a hot gas giant 700 light-years away. That one single result proved the concept. It wasn't just hype anymore. Webb could read alien atmospheres. And then it went further. Webb found water vapor on WASP 18b, WASP 80b, and GJ 486b. These aren't friendly planets. One's boiling, one's practically hugging its star. But the point isn't that they could host life. The point is that we could read them, measure the thickness of their clouds, track changes in pressure, see signs of things like methane and sulfur dioxide, gases that mean something when they show up in the right combinations. Then came WASP 17b, and that's where it got weird. Webb didn't just find vapor or gas. It found solid particles in the planet's sky, tiny silicate crystals, essentially glass, suspended in the atmosphere. The same way Earth's clouds can carry water droplets, this planet was flinging microscopic quartz around like hail. It was the first time we'd seen anything like that. And it made us realize something: exoplanets don't follow Earth's playbook. Their weather systems, their skies, their entire logic might be different, wildly different. And Webb was the first tool that could actually show us. But it didn't stop with exoplanets. Webb turned its gaze inward too, toward our own solar system. And even though these were closer targets, it still managed to surprise us. It captured the sharpest view of Neptune in over 30 years, not just the rings, but the thermal profile, the pole, the cloud tops. The level of detail was unreal. Then it locked onto Chariklo, a strange asteroid with its own tiny ring system, and detected water ice. That's an object only a few hundred kilometers wide, yet Webb could map its surface. Then it turned to Europa, one of Jupiter's moons, and detected plumes of water vapor venting into space. That confirmed what we suspected from older missions like Galileo and Hubble. But this time, it was crystal clear. Europa wasn't just frozen. It was active, breathing, jetting out the contents of its subsurface ocean like a leaky faucet. And Webb was watching it happen in real time. Even Comet 238P Erid, a small rock in the asteroid belt, got its spotlight. Webb detected water, but no carbon dioxide, which was weird. Most comets have both. This one didn't. That tells us that maybe this comet formed in a warmer region than we thought, or that its core has long since escaped. Either way, that's a clue about comet formation, about solar system chemistry, about how water made its way here in the first place. And then there were the trans-Neptunian objects, icy bodies way out past Pluto. Webb started picking up traces of methanol and organic compounds on them too, helping us piece together what the outer solar system was like in its earliest days. These weren't just static leftovers. They had chemistry, change, history. So yes, James Webb was built to look far, but it turned out to be just as powerful when it looked near. Because every time it focused on something we thought we understood, whether it was a planet we'd already discovered or a moon we'd been circling for decades, it showed us something we missed. In 2023, JWST started pouring in data from deep field surveys. One of the first things astronomers noticed was the sheer number of galaxies it was picking up in the first few 100 million years after the Big Bang. Not just faint blobs of light, not background noise, fully formed galaxies, dozens, then hundreds, in places we thought were still empty space. And some of them were just wrong. Take CERS 93316, for example. Based on its redshift, it looked like this galaxy existed just 235 million years after the Big Bang, the farthest galaxy ever observed at that point. That's way earlier than we expected anything that complex to exist. And it wasn't alone. Webb kept picking up more like it, bright, compact, well-structured galaxies that didn't look like they were still forming. They looked done. And that was a problem, because to make a galaxy like that, you need time. You need heavy elements. You need stars that live and die and explode and recycle their guts into the next generation. You need dust and gas and rotation and gravity all working in sync over hundreds of millions of years. But these galaxies didn't have that kind of time. So something wasn't adding up. Were these galaxies somehow forming faster than anything we'd ever seen? Were they forming differently, skipping steps we thought were necessary? Or was our whole timeline for the early universe off by a wide margin? And then Webb found something even stranger. The JWST Advanced Deep Extragalactic Survey, JADES, one of its largest deep field imaging programs focusing on the Goods S and Goods N fields, offered detailed images of galaxies at high redshifts. These observations were expected to refine our understanding of galaxy formation and clarify how supermassive black holes achieve their enormous masses so early in cosmic history. However, a surprising discovery from JADES data has challenged fundamental assumptions about the universe's structure, specifically, the principle of isotropy, which posits that the universe should appear roughly the same in all directions with no preferred orientation or spin. In a study led by Leo Shamir of Kansas State University, researchers analyzed 263 spiral galaxies in the Good South field using the Ganalizer algorithm, which assesses galaxy spin direction from radial intensity plots. The results revealed a striking asymmetry: 158 galaxies, 60%, rotated clockwise, while 105, 40%, rotated counterclockwise. This imbalance hints at a possible preferred spin direction in this region of space, challenging the notion of a directionless, homogeneous universe. Previous studies have noted similar spin asymmetries, with the effect appearing more pronounced at higher redshifts, suggesting a potential primordial structure in the cosmos. Some speculate this could align with physicist Nikodym Poplawski's unconventional theory, which proposes our universe formed inside a rotating black hole in a parent universe, possibly imparting a directional spin bias to cosmic structures. However, Shamir's team offers a more conventional explanation. The asymmetry might stem from a Doppler effect bias. The Milky Way's motion could make galaxies spinning opposite to our perspective, clockwise from Earth, appear slightly brighter due to blue shift, potentially skewing automated classifications. The small sample size of 263 galaxies and the challenges of imaging faint, high redshift objects further urge caution. Larger, more diverse datasets from ongoing JWST observations will be crucial to determine whether this asymmetry reflects a true cosmic phenomenon or an observational artifact.